Welcome to another deep dive. And listeners, get your philosophical hats on, because today we are going deep into the fascinating world of the philosophy of chemistry.
The deep dives it will be.
Yeah, really a realm where, we start to ask really profound questions about the nature of matter itself and how it all transforms. And, as philosophers, we bring, I think, a very unique and kind of, a really potent way of looking at these foundational concepts.
Absolutely. And I think it's important to remember, we're not just taking philosophical ideas and slapping them onto chemistry. This has been a real dialogue. Since the beginning of both, really. Chemistry, in a way, has always had to grapple with these big questions that philosophers love to talk about. The nature of reality, what is the world made of, all that good stuff. So really what we're doing today is trying to bring out that philosophical dimension that's already inherent within chemistry and make it a little more explicit. For all you philosophy fans out there.
Exactly. So let's lay out our philosophical workbench here. What are the tools? What are the materials we're going to be working with? And, a lot of it is going to be these really core conceptual puzzles that come right out of chemistry. What is a substance? What makes something an element? The implications of atomism, the idea that everything is made of these tiny particles. And then that ever-present mystery of the chemical bond. What is holding these things together?
Right. And then taking that a step further, thinking about how these very specific chemical ideas then bump up against these broader themes in philosophy of science. So, talking about realism, what can we really say exists in the chemical world? Reduction, can we just boil everything down to physics and say, well, chemistry is done, or is there something unique about it? And then, of course, how do we explain things in chemistry? What are the roles of models? How do we confirm our knowledge? All these classic philosophy of science questions, but, seen through a chemical lens, which I think will be really interesting for, as you said, our philosophically inclined listeners.
Right. And I think, sometimes people might think, the philosophy of chemistry, that's kind of a new kid on the block.
Right.
And philosophy of science, relatively new. But, it's not just new. This has actually been going on for a very long time.
Oh, yeah. While the formal specialization is somewhat recent, if you look at the questions that philosophers of chemistry are interested in, these have been debated for literally centuries. Going all the way back to Aristotle, that's where a lot of this starts, 4th century BC. He's writing about what we would now think of as chemistry.
Yeah. So really, it's this deep dive is about tracing how chemists, over time, have struggled and wrestled with these really foundational questions about the very fabric of reality. And how do their approaches, which are often so grounded in experiments, doing stuff in a lab, how do they compare and contrast with the more kind of abstract, philosophical ways of inquiry? And hopefully, by looking at it through these two different lenses, we'll get a richer perspective on both. Okay, so let's get into the real nitty-gritty here, starting with those basic concepts, substances, elements, and how they all kind of fit together.
Yeah, so we'll start there because it makes sense.
Right.
Our whole notion of chemical substances today is so tightly bound up with the ideas of elements and atoms. We think of everything as being made up of atoms, of elements, like hydrogen, oxygen, whatever. And these are seen as these kind of little micro primitives.
Right.
Like the fundamental units of chemical analysis. But, it took a really long time for people to actually accept that these chemical atoms were real things. And even something that sounds so straightforward as, saying, okay, all substances are made up of elements.
Right.
Even that simple statement is actually super philosophically loaded, because then you start asking, well, wait a minute, what actually is an element? And then it gets really complicated.
It does. And, historically speaking, it seems like chemists have gone back and forth on how they even define what an element is.
Yeah.
And there seem to be these two main, ideas. We could call them maybe the end of analysis thesis and the actual components thesis.
Right.
So, end of analysis, kind of intuitively to me, feels like, okay, an element is whatever you can't break down any further.
Right.
It's that simplest thing that you isolate, and you can't analyze it into anything more basic.
Yeah. So, in a lab, an element would be that thing that, you throw everything you can at it, but you just can't split it up.
Right.
But then the actual components idea is a little bit more theoretical. It says, okay, elements are these fundamental things that actually make up all the other stuff. Even if we can't necessarily get them in their pure form, even if we can't isolate them, they're still in there.
Right.
So one is more about what we can do, the limits of our instruments. And the other is about this kind of deeper, what's it really made of, whether we can get to it or not.
Right, the essence of what it is.
Yeah.
And it seems like Aristotle, way back in the day, kind of leaned toward that end of analysis view.
Yeah.
but he had a really specific criterion for what made something a pure substance.
He did. And, for Aristotle, like a lot of modern chemists, the focus is really on substances.
Right.
What are they? How do they change? And he really dives into this in some of his key works, like On Generation and Corruption and Meteorology. And he was really wrestling with this idea of, like, what does it even mean to be a single pure substance? And his big thing was this idea of being homeomerous. And, that's a mouthful. Basically, it means made of like parts at every level. So if you take a piece of something, any piece, it's got to be made of the same stuff. So, like if you have a rock and there's a vein of diamond running through it, well, for Aristotle, that wouldn't be a pure substance because if you chop up the rock, not every bit is going to be diamond. Or if you have like oil dispersed in water or smoke in the air, that also fails the test.
Yeah.
Because it's not the same throughout.
Right. It gives us a very different idea of what pure means than like our modern chemistry definitions.
Yeah.
And his list of like fundamental building blocks, his version of elements was also pretty different.
Right.
He had this fire, water, air, earth, the classic four. Yeah. And it was all kind of understood through this concept of primary qualities. So can you unpack that a little bit?
Sure. So, he didn't just pick those four out of a hat. He was like, okay, I'm going to be systematic about this. He thought the most basic, like fundamental qualities of matter were hot, cold, moist, and dry,
Yeah.
kind of what you can feel. And each of his elements was like a combo of two of these. So fire was hot and dry, air was hot and moist, water, cold and moist, and earth, cold and dry. And he even uses these combos to explain, like why things are solids or liquids or gases. So like he thought moistness was what made something fluid, but then if it was also cold, you got a liquid like water. But if it was hot and moist, you got a gas like air. Makes sense, right?
It's really interesting, how he's trying to like build this whole system based on these like sensory qualities.
Yeah.
And when he talked about changes in substances, he made this distinction between like transmutation and proper mixing. So like, how did he see those as different?
Okay, so transmutation for Aristotle was more like what we'd call a phase change, like when water freezes into ice or boils into steam, it's still basically the same stuff, just in a different form.
Right.
But then proper mixing, that's where things get interesting. That's more like what we would think of as chemical combination today. You're taking different substances, like comparable amounts, and making something new.
Yeah. And this is where, a philosophical mind really starts to kind of see some divergence from our modern view. Because Aristotle, he thought that in this proper mixing, the original substances, they kind of contributed to the new compound, but they weren't really there anymore. Not in the way that we think of elements being present in like a molecule.
Right. So it's not like they're just little Lego blocks that get snapped together and are still there. It's more like they get transformed and their qualities kind of blend together.
Yeah. He thought they were only potentially present, right? Like they could be brought back under the right conditions, but they weren't really there as the building blocks. And why did he think that? I mean, it seems pretty counterintuitive to us now. Like, why would he say they're not actually there?
So there are a couple of reasons for this. The first one has to do with how he thought about mixing. He saw it as substances interacting and influencing each other. And when you mixed them, they actually changed each other. It's not just like putting them side by side. It's like they're having this little chemical conversation and they come out different.
Right.
Like he talks about how opposing qualities, like hot and cold, they kind of get neutralized when you mix them and you end up with this intermediate state. The other big reason is his whole thing about substances needing to be homeomerous. Remember, all parts alike. Well, if elements are defined by having these extreme qualities, like super hot or super cold, then a compound that's kind of in between can't really have those elements actually present in it. Because if it did, then every little bit of the compound would also have to be super hot or super cold. And that's not what we see.
Right. Yeah. So you'd have these like contradictions in every part of the substance.
Exactly.
Yeah. It's like if every part of a cake was as sweet as pure sugar,
That would be a weird cake.
it wouldn't work very well. So, okay, if the elements aren't actually there, just potentially, how do you get them back?
Yeah.
It seems like that would be a pretty big problem for this theory. In fact, the source even calls it the problem of mixture. So, like, what's the philosophical upshot of that problem?
So it definitely points to a weakness in Aristotle's model. It seems to work better for explaining how things get mixed together and reach a stable state where everything is kind of balanced. But then explaining how to go the other way, to unmix them and get back the original ingredients, that's a lot harder. It's not obvious how you would explain, like, separating salt from water if they've truly combined in this way.
Yeah.
But, this whole problem, it actually brings up this deeper issue that still pops up in modern chemistry, even for people who do think elements are actually present in compounds. And the question is, how do you define an element so that it makes sense both when it's on its own and when it's part of a compound? Because when it's combined, its properties can change a lot. So, like, how much can something change and still be the same thing?
Right. It's like the ship of Theseus problem, but for elements and compounds.
Exactly.
Okay, well, let's jump forward a few centuries now, to Antoine Lavoisier, often called the father of modern chemistry. And his way of thinking about elements, it was really different.
Totally different, yeah. He marks a real turning point. So we're talking late 18th century now. And Lavoisier, he starts putting together these lists of elements that look a lot more familiar to us today, like oxygen, hydrogen, and so on. Now, he wasn't perfect, of course. He still had things like caloric on his list and some stuff that we now know are actually compounds. But the big difference is that he was really focused on this question of method. Like, how do we actually figure out what the elements are? How do we determine the elemental makeup of stuff? And he was all about experiments.
Yeah, he was a real hands-on guy. And his famous experiments with water, showing that it's a compound formed from hydrogen and oxygen. I mean, they really highlight that shift in approach.
Totally.
Yeah.
Totally. He was meticulous. So he showed that, like, if you burn alcohol, you get water. But then he really carefully measured the mass of everything, the alcohol, the water, and he realized that something else had to be involved. Something from the air was combining with the hydrogen in the alcohol to make the water. And that something else, he figured out, was oxygen. And these experiments, they really brought to the forefront this idea of conservation of matter. This idea that you can't create or destroy matter, you can only change its form.
Right.
Which is a really big deal for understanding chemical reactions, and it's something that you don't see as much in Aristotle's work. It was a lot more qualitative back then.
Yeah. No careful measurements or anything. So this conservation of matter was like a key tool for Lavoisier.
It was central to everything he did. So if he was doing a reaction and the mass at the end wasn't the same as the mass at the beginning, he knew there had to be something else involved, even if he couldn't see it. And this led to his big definition of an element. He said it's the last point which analysis is capable of reaching. So basically, if you can't break it down any further using any experiments you have, then it's an element. So for him, it was really tied to what you could actually do in a lab. It's kind of like Aristotle's end of analysis idea, but now it's really grounded in experiments and this whole idea of conserving mass.
Right. And I guess, with those really precise measurements, you can really start to track things and make sure nothing was appearing or disappearing.
Exactly.
But, it's interesting. Even though he had this very pragmatic experimental definition, he still kind of speculated about some substances like earths maybe being compounds. So it's like maybe there's a deeper level of last point of analysis. Like maybe there's stuff we can't break down yet, but in the future, who knows?
Yeah, he wasn't completely shutting the door on that possibility. Like maybe there's a more fundamental level that we just haven't gone to yet.
Yeah.
It's like he's bridging that gap between the old way of thinking about elements and the more modern way.
Yeah. And then we get into the 19th century, and it's like a whole new ball game.
Right.
Because suddenly we have all these new elements being discovered. I mean, it must have been just mind-boggling trying to make sense of it all. And that's where Mendeleev and his periodic table come in.
Right.
Yeah.
It's a game changer. So imagine, right, all these new elements are being discovered, and chemists are starting to realize that there's got to be some kind of order, some system to all this madness. It can't just be random.
Right.
So people are trying to figure out how to organize it all, and Newlands comes up with his octave rule, which was a good start. But then Mendeleev and Meyer, independently, they come up with these really comprehensive periodic tables around 1869. And Mendeleev's 1871 version, that's the one that really took off. It was brilliant.
And it was all based on this really clever observation.
Right.
That if you arrange the elements by their atomic weight, suddenly these patterns emerged. Like elements with similar chemical properties would just pop up at regular intervals, periodically, hence the name.
Exactly. And at the time, there were only 63 known elements, but he arranges them by atomic weight, and boom, there it is, this beautiful pattern. And so he puts elements that behave similarly in columns, and he calls them groups.
Right.
But the really crazy thing is that his table had gaps in it. And Mendeleev, he was bold. He was like, those gaps, they're not mistakes. There are elements out there that we haven't discovered yet, and they belong in those gaps. He even predicted what their properties would be. I mean, talk about confident.
And it was spot on.
Right, spot on.
Yeah.
So then a few years later, gallium is discovered, fits perfectly in one of the gaps. Then scandium, germanium, all of these predictions, bang, 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 confirmed. It was a huge win for the periodic table, and it really solidified its place as like this fundamental organizing principle in chemistry.
It really is a testament to the power of careful observation and systematic thinking.
Absolutely. Absolutely.
And, Mendeleev, he wasn't just a great organizer. He also had some strong opinions about what these elements actually were.
Right. He did. He was a big believer in the actual components thesis. Like, he was convinced that elements were real physical things that were actually present in compounds. He didn't buy into that whole Aristotelian potential stuff. And that's why he used atomic weight to organize his table, because he thought the weight of a compound was literally the sum of the weights of the atoms inside it.
Yeah, like little tiny building blocks.
Yeah, exactly.
But then, the modern periodic table that we all know and love, it looks pretty similar with the groups and periods, but it's not organized by atomic weight anymore. Now it's atomic number. So what happened there?
That was a big shift. And it came about because as we learned more about atoms, we realized there was something even more fundamental than weight. It turned out that the way atoms behave chemically is really determined by their electronal structure, how many electrons they have and how they're arranged around the nucleus. And the number of electrons is determined by the number of protons, which is, of course, the atomic number.
Makes sense.
So IUPAC, the big chemistry organization, they made it official in 1923. Atomic number is the boss. And this change, it also helped to explain isotopes, which were causing some headaches before.
Right. Isotopes. Those pesky things that have the same number of protons but different numbers of neutrons? So like same atomic number but different atomic weight.
Exactly. And that was a problem when you organize things by weight, because then you had these elements that chemically should be in the same spot but had different weights. So what do? But with atomic number, it all works out beautifully. All isotopes of an element, they have the same atomic number, so they all belong in the same place on the table. And then, a few years later, the neutron is discovered, and suddenly it all made sense.
Right. The neutron explains the weight difference.
It's the missing piece of the puzzle.
It always comes back to the puzzle, doesn't it?
It does.
The source brings up Friedrich Paneth again, and his distinction between those two ideas of an element, the last point of analysis, and the actual components thesis. And he says something really interesting. He calls elements transcendental.
Yeah.
What do you think he meant by that?
Yeah, it's a very philosophical way of looking at it. So Paneth's point is that just saying an element is the thing you can't break down anymore, well, that doesn't really explain why elements have the properties they do when they form compounds.
Yeah.
If it's not actually present in the compound, how is it influencing its behavior?
Right. It's kind of a spooky action at a distance kind of thing.
Yeah. And so he's saying that elements are more like these abstract ideas, these overarching concepts that capture the common unchanging properties that we see in all the different compounds that an element can form. So like there these invariants, these essential characteristics that transcend the specific context of a particular compound.
Right. It's like they have this essence, this underlying identity that's always there no matter how they're combined.
Exactly.
And then we have Needham, who's a more contemporary philosopher, and he's pushing back on the whole IUPAC definition based on atomic number, especially with isotopes. He says, look, there are real chemical differences between isotopes of the same element, like reaction rates, even toxicity. He points to heavy water as an example.
Yeah, so Needham is making this really interesting point. He's saying, hey, these isotopes, they might be chemically different enough that we should actually consider them different substances.
Right. It's not just about atomic number. There are these real-world consequences to their differences. So he's kind of challenging this neat and tidy definition that IUPAC has put forward.
Yeah, he's like, the real world is messy, guys. You can't just define it away.
Exactly. But, of course, there are counter-arguments, right? I mean, the periodic table works so well, and switching away from atomic number would be a huge overhaul.
It would be like rewriting the chemistry playbook. Exactly. And there's the argument that atomic number is directly tied to electronic structure, which we already said is super important for how atoms bond. So, it's still an open question, what is an element? Even at that most basic level, there's room for philosophical debate.
Right. It's more complex than you might think. Okay, let's shift gears a little bit and talk about mixtures and compounds. We touched on Aristotle's problem of mixture earlier and how he thought about those things. But how has our understanding evolved, since then?
Oh, it's come a long way. It's really been a gradual process of taking those early intuitive ideas about mixing and then combining them with centuries of experiments and new theories. Lavoisier, he was key here again. His work on water, showing that it always has the same ratio of hydrogen to oxygen no matter how you make it, that was huge.
Right. That was like a big clue that compounds aren't just random mixtures. There's something more specific going on.
Totally. And then in the 19th century, Proust, he kind of formalized this observation and called it the law of constant proportions.
And that law became a big part of how we distinguish between compounds and mixtures.
Right.
So if something always has the same proportions of elements no matter what, then it's probably a compound. But if the proportions can change, then it's more likely to be a mixture, like a solution.
Yeah. But then there was Berthollet, who was like, not so fast. He thought that elemental composition could actually vary depending on the conditions. Like how much sugar you can dissolve in water depends on the temperature.
Right. So he's like, it's not always so black and white.
Exactly. And, for a while, it seemed like Proust was winning the argument. But then, in the late 19th century, this whole science of solutions started developing. And it used thermodynamics to explain why some things dissolve in others. And it turns out that, yeah, there is a difference between compounds and mixtures, but it's not always as clear-cut as the law of constant proportions might make you think.
So in what way did thermodynamics muddy the waters, so to speak?
Well, thermodynamics introduced this idea of an ideal solution, where everything is perfectly mixed and there are no interactions between the different components. But in the real world, most solutions aren't ideal. There are all sorts of forces and interactions between the molecules, and that can make the distinction between a compound and a mixture a little fuzzy.
Right. It's not just about, like, the proportions of stuff. It's also about how they're interacting.
Exactly.
And then there's these things called Berthollides, which seem to kind of vindicate Berthollet's point about variable composition.
Yeah, those are interesting. So Berthollides are compounds where the ratio of elements isn't always fixed. It can change depending on the temperature and pressure. And it turns out that, on a microscopic level, this is because of defects in their crystal structure. So there's a balance between energy and entropy going on, and that can lead to some variation in composition.
Right. So the law of constant proportions, it was a big step forward, but it wasn't the whole story.
Not the whole story at all. The real world is a lot messier.
And that messiness is what makes it interesting.
Absolutely.
Okay, so let's move on to another big topic, atomism. The idea that everything is made of these tiny, indivisible particles. And this is so fundamental to our modern view of the world, but it wasn't always so obvious. In fact, Aristotle, he had some pretty strong criticisms of this whole idea.
Yeah, he did. And they're really thought-provoking criticisms. He's like, okay, if everything's made of these atoms, what are the atoms made of?
Right.
Like, if it's just this uniform homogeneous matter, why does it stop being divisible at some point? What determines the size of an atom? And he also questioned whether atoms have properties. Like if an atom is hot or cold, how can that explain how a whole bunch of atoms together can change temperature if the atoms themselves don't change? But then if atoms don't have properties, how do those properties even come about when the atoms get together? Like where does the hotness or coldness come from?
Yeah, he's really pushing on the explanatory power of the theory. Like, can it really account for the diversity of stuff we see in the world and the fact that things change?
Exactly. And he brings up examples like, what happens when you mix salt and water, or how bronze turns green over time. Can atomism really explain these changes if atoms are supposed to be unchanging?
Right. He's like, you can't just rearrange these little unchanging blocks and expect to get all the variety and change that we see in the world.
Right. He felt like the atomists didn't really have a good concept of what a substance was.
Yeah. And then we jump forward to Robert Boyle in the 17th century. He's known for his experiments for making chemistry more experimental. And he also had this idea about corpuscles, which sound kind of like atoms.
Yeah. Boyle was definitely trying to move away from the purely philosophical approach and ground chemistry in observation and experiment.
A true empiricist.
Absolutely. And so he thought about these tiny particles called corpuscles. And he thought that different substances were made of different kinds of corpuscles, different shapes and sizes and arrangements. And he thought that could explain why substances had different properties. But, the source makes a really interesting point. Boyle's ideas about corpuscles, they didn't actually have much to do with his experimental work. Like his famous experiments with gases, they didn't really rely on those ideas.
Right. So it's kind of like he had this theoretical side and an experimental side, but they weren't really talking to each other.
Yeah. It's almost like they were separate projects. And even Lavoisier, who came after Boyle, he said that Boyle's corpuscle theory didn't really help chemistry advance that much. His critiques of the old Aristotelian ideas were more important than his own theories about corpuscles.
Yeah. It's like sometimes tearing down the old building is more important than starting the new one.
Yeah.
You got to clear the ground first.
Yeah.
So even though Boyle was a big deal for pushing experiments, his atomic ideas didn't really take hold right away. It wasn't until the 19th century, with Galton, that we get a version of atomism that really starts to make sense.
Right. So Dalton, unlike Boyle, he made some very specific assumptions about atoms. He said, okay, each element is made up of these tiny particles called atoms. All the atoms of a particular element are identical. They have the same mass and size. And most importantly, he said that his atomic theory could explain the law of constant proportions, which we talked about earlier.
Right. So he's tying his theory to something that's already well established, something that chemists are already using.
Exactly. And he even comes up with a new law, the law of multiple proportions, based on his atomic theory. He's saying that atoms can't be created or destroyed, they just get rearranged in chemical reactions.
Right. It all comes back to that conservation of matter idea.
Exactly. But of course, not everyone was immediately convinced. There were still some big controversies, especially when it came to actually figuring out how much each atom weighed.
Right. And this was back when, atoms were too small to see, let alone weigh individually.
Totally. So they had to figure out relative atomic weights, and they usually use hydrogen as the reference point. But figuring out exactly how many atoms of each element combined in a compound, that was really tough. And Dalton, he made some assumptions about these ratios that turned out to be wrong. Like, he thought water was HO, 1 hydrogen, 1 oxygen. Oops.
Little did he know?
Yeah.
Yeah.
And Berzelius, another big chemist at the time, he also criticized Dalton's theory. He said, okay, it tells us what's combining, but it doesn't say anything about how they're actually combining. What's the mechanism?
Right. Like, what's a glue?
Exactly. And Dalton, he tried to come up with explanations, like he had this idea about caloric atmospheres around atoms, but it wasn't very convincing. And then, to make matters worse, there was the discovery of isomerism.
Right. Isomerism. That's where you have two different compounds with the same chemical formula, the same number and type of atoms, but they have totally different properties. Right. Like dimethyl ether and ethyl alcohol, they both have the formula C2H6O, but one's a flammable liquid and the other's a gas.
Totally different beasts. And that really threw a wrench in the works for a simple atomic theory, because it showed that it wasn't just about what atoms were there, but also how they were arranged. And so chemists started developing these structural formulas to show these different arrangements.
Right. Like little blueprints of the molecule.
Exactly. And then it got even weirder with the discovery of stereoisomers. These are molecules that are like mirror images of each other. They have the same atoms connected in the same order, but they're arranged differently in 3D space.
Right. Kind of like your left and right hand. They're the same, but they're also different.
Yeah, exactly. And these stereoisomers, they could have almost identical physical properties, but they would rotate polarized light in opposite directions. So it was clear that the 3D structure was really important.
Wow. It's like chemistry was getting all philosophical and stuff.
Yeah, definitely.
And despite all these advances in understanding how atoms are arranged, there were still people who didn't buy the whole atom thing. Like Mach, Ostwald, Duhem. These were big names in science and philosophy. And they were still pushing back against atomism well into the late 19th century.
Yeah. It's hard to overstate how influential these guys were. And they had some serious objections to the atomic theory. Duhem in particular, he was very vocal. He argued that the whole idea of molecules as these stable, distinct entities was actually impossible, according to the physics of the time.
So they're like, the math doesn't add up, guys.
Yeah, kind of. And they saw things like valency, how many bonds an atom can form, as being these macroscopic properties that were being projected onto the microscopic world without any real justification. Like, how do you know an atom has a certain number of hooks? Just because it tends to combine with a certain number of other atoms. They also pointed out that you could do chemistry without believing in atoms at all.
Right. Like you can use the formulas and the laws and still get results.
Exactly. And their big critique was that, the atomists were basically defining atoms in terms of the properties of the elements they were supposed to explain. It's like circular reasoning.
Like defining a cake as something that tastes like cake.
Exactly.
So what finally convinced the skeptics? What was the smoking gun that proved atoms were real?
Well, it came from a very unexpected place. Brownian motion.
Right, that's that jiggling motion of tiny particles suspended in a fluid. Like if you look at dust particles in a sun,